The title of my talk, I want to just spend a minute talking about this. This is really about the scope. This is very much a visionary talk. It's going to be high level. I'm not going to have a whole lot of detail because there's a lot to cover. It's a 10-year vision, operational weather prediction, not research weather prediction, although both are complementary. Operational is much more, has much more stringent requirements, as you'll see. It's weather. It's similar to climate, but it's different. The time constraint is the most serious thing, but the number of scientific formulations that go on are a little different for climate than for weather. Prediction capability implies the entire system, not just the modeling component, but the end-to-end capability, and that's what we're interested in operational consideration, is how do we get from observations to output where users can use it. This talk will survey where we are today in our technologies and some of the modeling challenges we face with the technologies that we have. I'm an optimist, though, and I am optimistic with where we are and the kind of opportunities that are coming. You'll see as I go forward. So computing has been an integral part of weather prediction for almost 70 years. This is a picture of John von Neumann with the very first computer in 1946, and that was followed up in 1950 with the first weather forecast that was generated. It took a day to generate that forecast, and the forecast was for 24 hours. So it was not particularly useful, but it was useful in demonstrating that you could do numerical weather prediction, and this was a path forward. The path forward is measured by this graphic here that shows the NCEP operational forecast skill by a single metric, the 500 kilometer height. And that's a metric that you would use, but certainly there are others that would indicate whether forecast quality is better or not. What you see here is a steady progression, increases in resolution, which also leads to and requires an increase in the number of CPUs or CPU cores. Today we're between the 1,000 cores and 10,000 cores for running an operational model, a global operational model at the National Weather Service. Now, we continue to place a high priority on our weather prediction because we're seeing an increase in the number of billion-dollar disasters in the United States and around the world. Here what we see is an increase that goes well beyond what the average has been. This has been tracked for many years. And in fact, 14 of the billion-dollar disasters were recorded in 2018. 3 of them were large disasters, hurricanes on the East Coast, 2 of them, which cost $20 to $30 billion in damages, and then fires in the West was another one that was $24 billion. So there's clearly an economic motivation to improve our predictive capability so we have a better chance at being able to handle some of these weather events. Now, it isn't just the billion-dollar weather events. We can think, all of us can think, I think, of events around us in our neighborhood, whether it's droughts or floods or tornadoes or hurricanes. Those things are all there. It's part of what we live with. It's just that the frequency and the severity has grown. So here, the National Climate Center has tracked these billion-dollar events and does it every year. You can see the variety and the diversity of events happening all over the country. And let's see, anything I want to say about this? This is the 8th consecutive year of more than $8 billion events in the United States. So, and it's quite diverse in the types of weather events that happen. 49 inches of rain in 24 hours in Hawaii, 23% of the US in drought over the western United States, warmest year on record in Alaska, flash flooding in the Midwest, heavy snow in the spring, some of you may recall, in the east. So it's all over, it's diverse, and so the requirements on our weather prediction models only grows. We can't stop the events from happening, but we can, with good prediction, help to mitigate some of the impacts. So first of all is detection. It's the ability for observing systems to pick out, categorize events, to make predictions with our forecast models, and to disseminate that information to a diverse set of end users you see listed here. Forecast offices, fire weather centers, aviation centers, air quality, transportation, and water. And you see some of the impacts here with fire, with smoke, transportation for aircraft, and on-the-ground emergencies. Now, NOAA, National Weather Service, tries to cover a lot of these from short-term scales to long-term scales, from weather to climate, and provide advice in a whole host of areas. So what you see here is a list of models that show the different time scales they're associated with, from minutes to years to centuries. And there's many types of capabilities that they're trying to forecast. So it's diverse, it's difficult, but they're trying to stay on top of what are the most important requirements. The most immediate ones are captured in our forecast models. We have a global prediction model that runs out to 14 days. That's the GFS today, soon to be replaced by the upgraded FV3 GFS. We have a regional model, which is North American domain, which is run out for 4 days. And then we have a finer scale nested model that is run at 3 kilometers over the US. And you can see those captured in these graphics here. Basic message here is the higher resolution you have, it means the shorter area that you can cover, and the shorter amount of forecast, smaller area that you can cover, and the shorter forecast that you can do. So predictability is somewhat dependent on the domain that you're trying to solve, and it's certainly constrained by HPC. This is the reason why we don't have high resolution global models, because we lack the computing today to do that. So what we do is we nest over the global model. We take the boundary conditions from the global model and provide them to the regional or local scale model so that it's got sufficient information to be able to progress or make predictions at the smaller scale. Now, you can't run for very long because the boundaries get polluted by not having up-to-date information, and so the model starts to lose accuracy. You can see here is a number of experimental nests that are going on within our laboratory down to 1 kilometer scale to different size domains that are meant to serve specific weather needs. These models may run for 1 day, 36 hours, something similar to that. But the reason, again, is the trade-off that we have in limited computing for the time that we have to produce predictions. Now, improving weather prediction, you've seen this graphic perhaps in other talks today. I've seen it. We can increase the model resolution, we can increase the model complexity, or we can have more ensembles or instances of models that are doing slightly different calculations or providing slightly different input data, so we can see how each of the models might collectively provide insight, probabilistic information on the likelihood of an event happening. This decision that we make in whether to go with more complexity, higher resolution, or with more ensembles is really a trade-off between the computing that we have, the accuracy that we want, and the time to solution that we have to get the results. Now, what you see in the complexity is both climate and weather are listed here for components, and in fact, they're coming together. So a lot of what's happening in the full Earth system that would be captured in a more long-term climate model are being increasingly incorporated into weather prediction models. We go to finer scales as we look at being able to support higher accuracy in our prediction models. There are computational challenges that are significant, and it's caught the attention of a group that's been working on this since 2016. People from NOAA, NASA, the DOE, DOD, and Navy and NCAR have been discussing some of the challenges we face in our applications and have written a white paper, a position paper about our concerns. HPC architectures are developing in the wrong direction for state-heavy, computationally intense Earth system applications. So this is basically that we spend a lot of time working with memory and data, and we don't have a lot of compute to do on that data. So our concern is that the chips need to try to be developed in a way that would support, better support Earth system applications. We currently utilize, less than 2% of the peak performance capabilities of the chips. So it's great from a marketing perspective that we can advertise how powerful the chips are, but if they aren't benefiting our applications, then it's less useful. Certainly we're gaining benefit, but we are losing a lot as well. So surveying the processor technologies today, there's a diverse set of them out there and more on the horizon. CPUs, GPUs, TPUs, FPGAs, ARM processors. It's quite diverse. Many types of processors, lots of cores on chips, different memory, different tiers. It puts a lot of burden on the compilers, on standards to be able to support portability, performance, and interoperability. So this is a challenge from the application standpoint, what we do here, and this is not easily solved, but it is one that we're aware of as we develop our applications to be able to try and have a goal of performance portability. Not all models do, but there are some success stories out there. Now, when you go from processors, which are the easiest way for you to do comparisons between the value of one chip over another, you really can't do that because processors live on a node. They're packaged in a way, typically it's a dual socket CPU type system. There might be attached accelerators on there. There's increasing diversity here as well in the number of sockets, the number of processors. That we can have as many as 10,000 cores, as you see on a dual GPU type system. Memory is also quite diverse. And communications within the socket, between nodes, so intranode, and being able to communicate with the file system. There's many vendors, many choices. We have performance considerations, energy, cost, those sorts of things. So this is also a challenge, but it is nice to see that there's competitiveness out there and that we're seeing that there's decent price performance metrics that we can at least rely on for our HPC choices. Now in terms of application performance, we do it typically with a node. This is single node, so there's no communication off of a node. This was a research model that was developed at NOAA in the laboratory I worked at until 2016. It was experimental. This is a directive-based solution using OpenMP, OpenACC, and so an internal library that supported translation for MPI-based parallelism, distributed memory parallelism. The model itself, called the NIM, was performance portable and demonstrated for the different generations of GPU and CPU, as well as the mic processor technologies for the years that they came out. A very nice way to show to the vendors how they were doing with this application. And in general, we were seeing between 2 and 3 times performance improvement for this model. It used a uniform icosahedral grid, which was very nice in that every calculation could be identical anywhere on the domain. Rich is going to talk about the MPAS model, I'm sure, in the next talk. This model was developed at NCAR. It's been adopted by IBM Weather Company. It is showing performance results that are quite similar to the NIM model that I showed you before. And in fact, a lot of the design of this model, the MPAS model, is quite similar, if not identical, to some of what was put into the NIM model. So there was some benefit there in being able to help make this model be performance portable. Use directives as well, performance portable, and showing nice performance. So that's very good. It's a very good statement for OpenACC as well that was used for the GPU parallelism. The FV3 GFS, this is single node performance here as well. This has been selected, as I said, by the National Weather Service. It was designed for the CPU. It's efficient in using the memory, the large cache memory on the CPU. However, it's slower on the GPU, and this was really the first time that we'd run into such a performance degradation. What you see here in blue is the CPU performance, and then in the orange is the GPU performance. So it was significantly worse, and we did some work to reorganize the memory so the loops could be done in a different way. But we didn't see any super success, and we certainly didn't see performance portability. There are some fundamental issues that need to be overcome in the design of this model. There's limited parallelism available for the GPU. It doesn't use a uniform grid. It's a cube-sphere grid, and there are implications there in how we have these special cases for certain cells that are close to an edge or a corner of the grid, and those that are in the center. There are special cases on the edges, and that means scalar operations as opposed to parallel ones. There's ongoing efforts by other groups to address the performance challenges that are there in the FE3 GFS. Going on to more advanced node technologies, you've heard about the DGX2 with 16 GPUs available connected with fast bus, 8 connections off node to support having this connect to other potential DGX nodes, and I'm told that there's actually more of an HPC offering now from NVIDIA as opposed to the DGX line. Summit, which is the largest DOE system, the largest system in the world available, has a dual power CPU with high-speed connectivity between the CPU and the GPU using NVLink. So that represents a view of nodes and node capabilities that are quite fat in terms of lots of compute power that are available for these nodes. That has its own implications in terms of balance in the system. So when you want to connect these very fat nodes together, you have to go outside of the node across an interconnect of some sort through a switch. And the capabilities for the interconnect are lagging. The improvements that we get in the CPU and the GPU processing capabilities is far greater than the improvements that we see on the interconnect. In addition, the applications have to use MPI, so there's extra operations that need to be done, and that takes time. There has to be synchronization, so if you need to do communication, you have to wait for the slowest one to complete its communication before you go on. There are techniques that you can use to hide the communications cost. Those would be built into the application. But scalability overall here, when it comes to big systems, is a big challenge for maintaining application performance. So other groups have recognized this, and there was a scalability program at the European Center in England to address this scalability program. And there have been a number of projects that have been part of that to address and look at scalability and how can we overcome some of the challenges that they're seeing and that we're seeing in terms of scalability as we go to very high resolutions. In the cases you see here, this lower plot here on your left is showing the IFS, which is the current operational model ECMWF, running 1 kilometer. They're not doing I/O here. And in the upper right, various models to do different resolutions. So what you see out of here is that the metrics that are used are a little different than what we use in weather prediction. This is forecast days per day. Operational weather prediction requires 10 days of prediction for 1 day, 1 hour to 1.5 hour forecast. So that equates to 200 to 240 days per day. And here we're seeing in this low line, the low plot line, is the non-hydrostatic models that we run at the finer scales. That is showing we're about 30 forecast days per day. The other ones in the upper right, which you probably can't see, are similar for that sort of resolution model. So scalability is a concern. How do we overcome this is certainly the focus of many groups, including ours. So closer to home is the FE3 GFS strong scaling efficiency. And what you see here is a degradation in computational efficiency, which is a measure of how well you're using the processor when running the application, scaling to higher numbers of compute nodes. What I show here is compute nodes from, I believe, up to 256 nodes running the FE3 at the same resolution, so 14 kilometers with physics plus dynamics. And the efficiency really drops off. So we're at 40% efficiency, both in computation and communication, although we believe that most of this is coming from the communications and the effect of communications there. The factors that you consider that would slow down scaling are parallelism in the computation, how much of it's available, the algorithms themselves, and potentially the grid. I mentioned the cube-sphere grid, where there's certainly some scalar operations that have to go on there. In terms of communications, your considerations would be the frequency that you're doing communication, which you would send messages to another process, the amount of data that you're communicating, and how well you've been able to overlap those communications with computations. So if we look at using that to extrapolate FE3 performance, trying to get to a 3-kilometer global model, these are the results that you'd see. What you should know is that in doubling model resolution, you would provide 4 times the compute to maintain the same amount of workload and see how long it takes for you to get the run done, knowing that the operational time here for these 5-day runs is 2,250 seconds. So what you can see as we go up from 28 kilometers to 14 kilometers, those are the real runs that were made on our Theia supercomputer, and then extrapolations from there. This was a linear extrapolation based on the results that we got from these real runs. And what this shows is the time step also would decrease, so you would go basically half the time step because you need to maintain numerical stability for a prediction model. So you've got 3 things going on: increase in resolution in 2 dimensions plus the change in the time step. And the number of nodes that we see in this work would increase from 64 nodes to 4,096, which represents 98,000 CPU cores. And the runtime, which is shown in red, is well off of what the operational requirement would be. This is quite similar to what the European results were that I showed on the previous slide. So in order to go beyond this time, you would increase the number of processors, maintaining the same resolution in the model until you could get to the threshold of 2,200 seconds to run a 3-kilometer model in operations. And that's what you get here is, here we do strong scaling, so we decrease the amount of work per processor in order to complete in a faster time. And what you see here in red is that it would take 400,000 CPU cores to run a 3-kilometer FE3 model in operations. Now this is an estimate, and then certainly would be optimizations that could be done. But this is the reality for if you want to run a 3-kilometer model in the next 10 years with the current computing that we have today. This is really a mouthful to be able to understand how one might be able to afford the energy costs, to be able to afford the building, and the cost for procurement for this. So this invites at least consideration of alternatives. Now GPUs while they're faster, they still have the same problem when it comes to scalability. So here you see the time in blue in the upper plot timeline for the CPU. Now if you're able to double the capability of the CPU by buying GPUs, you still have the communications that you have to do. So that means that you're not doubling the capability in this example, the performance of the application. You're really only doing about 1.6 in this example. So because your communications is effectively going to stay the same. So that's one of the challenges that we have is scalability with the challenges with the interconnect, are not going to get us over the hump when it comes to faster processors. Faster capabilities on the node help us for sure, but it's not the total solution. There's more work that has to be done to hide communications and to find algorithms that will help us reduce the amount of communications that we need to do. Now, data challenges, I'm turning now away from the computational ones to the data challenges. Data is only useful if it can be used. So we have all sorts of observations. We have assimilation of those obs to provide an initial state for the atmosphere. We have the prediction that would be generated and output that's associated with that. We have to distribute that information and disseminate it to those that need it. There are a lot of different types of observations. In fact, more than we can use. There's new generations of satellites. There's all sorts of remote sensors. There's new generation radars. There's CubeSats. There's all sorts of capabilities that are out there on the horizon if they're not already here. And we're not able to use all the observations that we get. Now, the ground-based sensors were in better shape in terms of having a denser network of them. The satellite we don't use so effectively. It's more difficult to get the kind of information we need. But there are new instruments that are helping us there, but there's a lot more work that needs to be done to utilize these effectively. For the GOES geostationary satellite, you see the position, the relative position up in the upper right. There's two of them that serve the United States. They're basically satellites that sit in one spot and take regular measurements of that domain, basically the North American, South American domain. Right now, today, only 1% of that data is being used with the GOES 15 satellites. With the new satellites that we just launched that provide stunning scenery, views of the clouds and the storms and others, we're really not able to use that in our assimilation. That has 100x more data, but there simply isn't the capability in our prediction systems to be able to use them. When it comes to model output, going from 14 kilometer to 3 kilometer, you can do the math. For a variable, we have 64 vertical levels, and that would take about 1 gigabyte of storage per variable. If we go to 3.5 kilometers, it takes 21 gigabytes per variable. In a 14 kilometer run today, there's 10 main model variables, and we output every 6 hours. For a 10-day forecast, that's 400 gigabytes a run. For a 3 kilometer model, we would output the variables more often, 3 hours, every 3 hours. Still a 10-day forecast, 10 model variables is about 52 times more data that we would output in the model grids. That's what today is going across the wire to operational centers, weather prediction centers, and so on. What do they look like? Well, this is a diverse set of user requirements when it comes to distributing that data. We have National Weather Service forecast offices, Hurricane Prediction Center, Storm Prediction Center, National Water Center, Aviation Weather, and Fire Weather. Those are just the beginning. There's also state and local levels where this data in some form would go out. Within NOAA, National Weather Service, we rely on our own network to be able to send the data. It's called NOAA Port, and we distribute that to our workstations that are used for weather prediction. That's the AWIPS workstation. Others use this workstation as well. It's very flexible and provides a lot of value, but it has limited capability in terms of how much data it can store and the bandwidth of the network to get data to it is also restricted. The problem with this network is that everyone gets the same data, and they don't need the same data. What's going on in Hawaii has nothing to do with what's going on in the Northeast. But we have that restriction, and it's partly due to a legacy. You know, the old days, when there wasn't so much information being distributed, we could get away with that. But we need to be looking at how data is being distributed to be much more effective, especially in the era of huge data volumes that we're seeing in our prediction models, in our observing systems, and so on. So the state of play, where we are today in our computing and our applications. The science advances are increasingly constrained by computing and data. There's no expected increases in processing speed. We know that. The chips aren't getting faster. There's limited increases in the memory speed. We may get some, and we're certainly pushing on the vendors to support us there. There are parallelism and scalability limitations in the applications, and there's an operational time constraint. For the data, there's too much data for us to process, so we don't do that. Satellite data I showed you, we process about every 100th point. There's too many observations to use, and it's too large to distribute. So it's pretty grim. As I said, the prediction in looking out 10 years in the way that we are currently doing things and the HPC that we have available is fairly restrictive. So what do we do? Where do we go from here? We have to look at this as a whole system, end to end, from the data to the stakeholders, the end users. And we have to think about systems and design and technologies that are going to incorporate and take advantage of those technologies in solving each of these pieces, either collectively or individually. I first learned about this technology convergence at International Supercomputing last year was this, and I hear it more and more, and I think it's got a lot of opportunity for us in our traditional supercomputing, machine learning, and big data. There's a convergence there, and science in this space sits in between. So there's opportunities for us to do more with these different technologies and capabilities that are there. So I'm going to go into a little bit of that. There's work going on in my team that, and elsewhere that I'll reference that are attempting to get our hands on how do we improve the efficiency of our prediction models, how do we get data distributed in a more coherent way, how can we be smarter with how we build our prediction systems so that they serve all of us. Number one, improve model performance. This certainly underlies what we consider forecast accuracy. It relates to higher resolution, more science, and potentially more ensembles, as I indicated before. So our studies are, in terms of quantifying scientific accuracy versus computational efficiency. So how can we use the computing capabilities as efficient? What sort of algorithms are the ones that are the best? And so we can look at the prediction models that are currently in being used right now or being developed, and we think, well, what are the best features of these models and approaches that they've chosen? Do we have an indicator of what we might do for the next 10 years in focusing on what the best predictive capabilities might be, given the computing that we expect there to be? So we're looking at algorithms, we're looking at grids, we're looking at time step. So time step is a really critical one for us, is that when I showed that plot with the scalability for the FV3, we have the time step for each increase in resolution. But there are methods that will help extend the time step, and they're semi-implicit methods that look attractive. There's a very nice paper down here at the bottom that describes the work that's going on for time integration, different choices that modeling groups are making and why. And certainly that relates to a lot of the other decisions that are being made here in terms of the choice of the algorithms that you would use. So these are all areas that research groups are more active in researching what the best choices are, and we're certainly there with them. So ECMWF, as I mentioned before, had this concept of dwarfs, climate or weather dwarfs. They encapsulate some capability within the prediction system. They pull it out of the model that they have, and mostly that work has been with the IFS. They extract it, and then they explore alternatives, and they look at portability and hardware and design so they can come up with better ways and ideally integrate that back into the modeling system. So that's the concept of a dwarf. They're doing it more within their own operational system and less of an open mind to different choices that they could make. But they're still doing very good work here, and we're collaborating with them on research results that they get. We're doing a similar thing, but maybe more comprehensive in that we've developed a framework in which we can explore the different alternatives in the grid design, the time stepping, and the type of algorithm that would be there underneath, and try to quantify the computational efficiency versus scientific accuracy of these choices, and then try to narrow down on the ones that look the most appropriate. So we're using C++ for this development to define communications, the grid, the type of discretization, and time stepping operators. There's all sorts of choices that go on underneath as well that I won't mention here. And the goal is to use OpenACC and OpenMP and to evaluate performance, portability, and scalability to 1 to 3 kilometer on CPU, GPU, and other architectures. So we're trying to go into this with a lot of investment up front to build this framework. We're about to a place where we can start running and publishing some of the work that we see in comparing the different approaches. We're starting with advection. We're going to add in convection and radiation as we try to build the nucleus of what we think would be a prediction model that will support further research as we look 10 years down the road. Another area that we're doing work is the shallow water model is being used. We have a Dwarf that's looking at grid staggering. So this is an area that we have seen there's more computational complexity, more memory, more communications requirements potentially for the C grid staggering versus A grid staggering. This is the way in which information is located on the grid cells. And so we're trying to quantify here again the performance scaling, scientific accuracy. And as my colleague Jacques Middlecoff put it, if we're able to run, we're able to have a more efficient solution, then a fair comparison would be running at a higher resolution for the less accurate one. If it turns out to be more efficient, then what is it that we can do to have the same accuracy, compare this based on accuracy. So accuracy would be that we know that the C grid is more accurate in many ways, but it takes more compute. So if we get more compute and run at a higher scale, will the A grid achieve the same accuracy or more? These are things that we'll be looking at. So we expect some publication results sometime this year on that. So in looking at dwarfs and scalability, this is a sort of scaling pattern in contrast to what you saw with the FV3. Efficiency here, which is in compute, is shown as to be super scaling for this fairly small model. That's not so surprising if you're using memory efficiently. The communications you can see dropping off in red, that is expected, but you can see that the total runtime, which is in green, is fairly close to the compute time. And that means that the communication is not having a severe impact on the overall performance. That's a good thing. So this plot actually is quite promising in what we've been able to achieve here. For this small dwarf, it has good parallelism. It's using a uniform icosahedral grid, and it has an algorithm that's efficient. Communications, we've been able to minimize the frequency with small amounts of data that are being sent, and some overlapping is being done. So this would be a target. This is what we have in mind for some of the comparisons that we would do. Now, in terms of physics, a lot of the code in weather prediction is in the physics. There's an awful lot of calculations that are being done there. Convection, radiation, microphysics that you've heard about earlier today, surface and boundary layers, gravity and orographic wave drag. These are things that are part of a physics package. They're computationally complex and expensive. They use a lot of data. And it seems like a prime candidate for machine learning, deep learning capabilities. It's still early in terms of what we can get out of it, but some work is begun. I've referenced some work that others have done, but we're starting to look at this as well, because we think that if we're able to run the physics and parameterizations hundreds of times potentially faster and integrate that successfully into our prediction models, that'll be a real good step up for us in using AI to advance the capabilities of our models. In terms of chemistry, we don't hear a lot about it except when there's a fire, and there's been a lot of them lately. This particular fire, which was the campfire in California, was just amazing, moving 80 football fields per minute. So this fire moved very, very fast. And this is a satellite picture of this as it was developing. So one of the things that we are looking at is how to, once the smoke gets to be too dense, you can no longer see the fire. So you want to still be able to provide some accurate predictions so that firefighters can go in there to the right locations or know what's going on in the fire. And so there's some work going on to use machine learning, deep learning, to be able to incorporate an estimate of where the fire is, even if you can't see it from because the smoke is obscuring the view from the satellite. Number 2, improve data assimilation performance. This may be an area, data assimilation, where we can make the most gains in terms of our prediction capability. I'm doing okay. 1 minute? I'm only showing 40 minutes. Okay. Really? 1 minute. Okay. I'm going to have to briefly go through this. So assimilation is a fairly complex process where we're taking the observations on the left and trying to incorporate them into the model on the right. And that means that we've got to do a lot of estimations, interpolations, and so on to adjust the values of the data. And so once you adjust a point, you've got to take into account all the surrounding points and what the impact is there. So it's fairly complicated. I'm going to skip over this. This is a new assimilation, JEDI, which is being developed by the National Weather Service. By the NESDIS, which is part of NOAA. Computational issues in terms of the different approaches that you take with assimilation. There's some research that's going on here in using, improving the capabilities of our assimilation system. Again, scientific accuracy versus computational efficiency. Soil moisture, we're doing work with machine learning to improve the estimate for soil moisture, and that's for the operational prediction model. We've done, David Hall spoke a little bit about this and showed, I think, this same video. He's been working with us on this, is to use machine learning AI to be able to identify typhoons. So getting data to end users, this is the bottom line, is that when you've got disasters of some sort, you need to be able to get the data there. I've got 2 slides. So big data handling, there's a timeline for this. The data's got to get out there. The information's got to get out there. And so you could conceptualize that you have some sort of cloud capability that will allow you to scale up as you need to when disasters are happening. In one area, you have the compute that's to do it. You co-locate your HPC with your data resources. You provide observations and others in there for processing. And then you have your machine learning, your analytics, your informatics to be able to provide information. You don't necessarily need grids at the local weather service office. You need information, you need insights. You might need pixels, but you don't need the grids. And if you do need the grids, you only need a small amount of them. So the idea would be that you try to use tools that are living in the cloud or that are local to your desktop that are capable of transferring only small amounts of information tailored to what the end user wants. It's very much a demand-driven capability. So improved software process is number 4. This is something that's been used in industry for a long time. We have really a very poor software process in general. It's not that hard, but it is a cultural thing for us to do, which is design, develop, test, commit, and then refactor at times. These operational codes are millions of lines, and they're very hard to move around. They're very hard to work in. People have developed them 20 years earlier and have retired. So all of these things are impediments for us to be able to advance our prediction models. This is an example of it with a JEDI software architecture. They're going about this in a very nice way with object-oriented C++ at the very lower end. The upper end is Fortran or application code that's written in some way with some ways in which you interface down into this JEDI layer. Everything is very clean. They have a clean software process, so they're very good with that. So in conclusion, I've described very quickly, there just simply hasn't been enough time to be able to go through this as much as I would like. Describe the challenges that we have in our current prediction system. I think we've got tremendous opportunities in terms of the convergence of HPC, big data, and AI. NVIDIA GPUs are certainly a key technology in this, being able to support us in a number of ways. So we certainly, for me, this is my 12th year coming here for this conference, and we continue to see that NVIDIA has got a lot of important contributions to make for us at the NOAA, National Weather Service, and in research. There's I/O challenges that I didn't mention, sensor networks, and assimilation techniques that could distribute the way that processing is done. We're early in our investigation for AI. There's a lot of promise out there. There's some work with references that are shown, as well as a conference that NOAA is organizing in April. So that's it. Thank you. I'm sorry I had to cut short.
Yeah, thank you.